Hello, so I've been asked to solve this question by using, but without using the Pythagorean method. Because this question right here, determine the x-coordinates for the points of inflection for the first function. This is considered solvable through the Pythagorean identity, which is sine 2x plus cos 2x is equal to 1. But it can be solved without that, by using the unit circle instead. So I'm going to show the method on how to solve that. So, first, we need to know the points of inflection for the function. So at point of inflection, f double dash, or in this case y, so y double dash, equals 0. Not y double dash, y double prime, whatever you want to call it, second derivative of y is equal to 0 at the x-coordinates for the points of inflection. This is also quite useful because it asks for the x-coordinates, not the y-coordinates also, so we don't need to sub them back in. I guess that's why it's a limited working space. Anyways, so for the first derivative, we're going to just be, so also consider that sine 2x with this 2 is equal to y equals sine of x squared. Just something to know. It just makes it a bit easier to know to use chain rule. So it's just say using chain rule. And I'm just going to do chain rule by inspection, which, well, I hope we all know how to do by now. Nearing the exam in a couple, well, less than a week, is it? No, just a lot over a week. So this is going to be 2, so the, I'll just zoom back in. So this is going to equal 2, which is the index, the power, multiplied by the inside function, so the differential of sine x is just cos x, multiplied by the outer function, but subtract 1 from here, so I'll just do that. So sine x is to the power of 1, but we'll just call it sine x. So let's just simplify this, so I'll just go over here, 2 cos x sine x. So that's our function for the first derivative. Now let's take the second derivative, because we aren't looking for horizontal points of inflection. If we were looking for horizontal points of inflection, we would need to use both the first and the second derivative. But all we're using the first derivative for is to find the second. So let's second derivative now. So this is going to, so we're going to need to use the product rule, because we have two functions with x. So let's just do that. So it's v u dash plus u v dash. U is going to be our first function, and v is going to be, so u is the first function, and v is going to be our second function. So u is going to be equal to 2 cos x. So that means u prime is going to be equal to, the differential of cos is negative sine, so negative 2 sine x. And now our v is going to be equal to sine x, our second function, which means that v prime is going to be equal to just this differential of this, which is cos x. So now let's sub these in. Y dash dash is equal to, so v sine x, u dash, so negative 2 sine x, plus u, so 2 cos x. I'm going to just shift all this over a bit so I can fit it all. I'll just leave this here, so just out the side. Actually, yeah, I'll zoom out a little bit and then leave it there, just so it can be seen right there. So, and then plus v dash is this cos x, so cos x. Now if we simplify this, I'll just do it in the line beneath, so we're going to get negative 2 times sine x squared. So it's going to be negative 2 to sine x squared plus, and then 2 cos x squared. Yeah, multiplying the causes, multiplying the sines, right? And we can take 2 out of this because there's 2 on each term, so we can take 2 out. But we should also write it so instead of having a negative here, we can just turn this into a subtract. So we're just going to put these two terms on opposite sides. So let's just do that and take the 2 out at the same time. So take the 2 out, put the positive term first, so cos x squared, cos 2x, we'll just call it that, instead of doing the squared, minus sine 2x. And this equals 0. Now that we're looking for the horizontal points of inflection now, the e point, the second derivative points, as this will equal 0, we can divide this by 2, divide this by 2, these cancel, which will leave you with 0 equals cos x, because remember cos 2x is equal to cos x squared, minus sine x squared. Now that we have a subtract here, we can just add this to the other side of the equation. So then we'll end up, I'm just going to put it over here to save some space. So this will be sine x squared is equal to cos x squared. And now because these are, both these are equal, we can take the square root of both sides. And what that will do is that will just cancel the square and the square root. And that we've taken the square root of both sides. So we end up with sine x is equal to cos x. Now, now that we haven't used the Pythagorean identity, but we still want to find the x points, what this equality here pretty much means is that we need to find x points. So this will only happen at certain points of x, which means that x will have many solutions. And that is because these don't equal each other at all x points. Only at specific x points will these equal each other. So, because I'm not that good at drawing, I've gotten myself a chart of the unit circle, very fancy. I'll bring this up here a bit, little reference. Now, let's just bring this down here, and I can demonstrate what I mean by trying to find x points. So sine x equals cos x. So this is the equation we need to find, and this is the unit circle. Now, the only way I'm going to demonstrate is how to use it with the unit circle. You can do it with special triangles and such, but it's just significantly easier to do. So if you want to draw your unit circle out, if you actually want to draw it, I'd recommend just doing the first quadrant, you know, this basic thing, 1, 3, 2, 2, 3, 1, over 2, over 2, whatnot. Just doing this thing, and then the square roots on top, so square root, square root, square root, that kind of thing, just the general unit circle, but because I don't want to do that, I just have this chart here. So, what we're pretty much looking for is points of x where both of the coordinates are equal. So, for example, they wouldn't be equal here, because at x equals 0, right? At x equals 0 here. So this is just an example. At x equals 0, sine of 0 is going to be equal to the right coordinate, which is 0, and then cos 0 is going to be equal to 1. Equal to 1. So now, with this, 1 is not equal to 0. These are just not equal, which means that x is not a valid point that we can use. So this is using both of these coordinates here, so let me just erase this a bit. So that's just a small situation to demonstrate what I mean. So we kind of had to find points, x points, where both the coordinates are equal. They're not equal here, they're not equal here, but they are equal at these points, as you can see. So at pi over 4, at pi on 4, sine of x is equal to cos of x. If that makes sense. Because sine pi over 4 is equal to root 2 over 2. Sorry. And then cos pi over 4 is equal to root 2 on 2. As these are equal, this is a valid x point at pi over 4. So, and knowing that, because this is in not a single rotation yet, but this is in the unit circle, we know that the unit circle is symmetrical around. So at pi over 4 is a valid point. See, these are also equal at 5 pi over 4, which would be another solution. Because these are both positive, these are both negative. The solutions are still the same. So at x equals pi on 4, and x equals 5 pi on 4, These are both valid solutions. I'm unsure if the marking guide accepts these points, because technically they are not equal here. But another thing to consider also is that these points, if you go back up to here, what the equation was, it was sine squared x equals cos squared x. So from this, because this equation here is the simplified one that we derived, but if you look at, because we just took the square root of both sides, but if you remember, square roots have plus or minus answers. So, for example, the square root of 4 is actually equal to plus or minus 2, because negative 2 squared is equal to 4, and positive 2 squared is equal to 4. So therefore you have the two positive and negative solutions. So, knowing that, because these are both, because if you, if you take these x points and you put them in, if you square these, no matter if they're positive, as you see these are positive, or negative, so one of these are negative and one of these are positive, they're both going to end up being positive. So that is why it's not just x equals pi on 4 and x equals 5 pi on 4, but also these quadrants here. Not quadrants, but points. Because at these points, because they're both squared in the equation, so because these are both squared, these end up being positive and these both being positive and positive. And same with the negatives both end up being positive also. So that means valid points are these both, but also these points, 3 pi on 4. So x equals 3 pi on 4, and x equals 7 pi on 4. So these are going to be your points. The reason why we aren't continuing to spin around the circle, because you can do this, you can keep coming up with solutions, is because the domain given is 0, x, 2 pi. And this is the last rotation before you go over 2 pi, which is not what we want. So these are going to be the solutions for that question without using the Pythagorean identity. The reason I think this method's faster is because if you can draw one quadrant of the unit circle, so you draw your one quadrant and understand this, if you understand this root 2 over 2 aspect, how these are the same, at that point, it is significantly faster than substituting the identity. Even and also because the identity isn't done as much as it could be as a topic of as subject matter. I don't think it's taught enough as it should be, because well, at least in my class, we haven't gone over it really that much at all, and have only really touched on it now. So because of that, I do think that this method it's easier to understand, in my opinion, and it's a lot easier to do. Because you can actually have a basis on why it works, and you're not just kind of copying down a formula out of the formula booklet, if that makes sense. So it's easier to understand where it's used also. But yeah, that is my solution for this problem. Now part B also asks, I'm not really going to get into a lot of detail with this, but it kind of just says, evaluate the reasonableness of your solutions to 17a by referring to the concept of concavity. Know that your concept of concavity changes when the point of inflection, at points of inflection. So for example, if you take your cubic graph here, this is just an example, because the point of inflection is right here, right? This is your point of inflection. POI is at that point, and that is because as your graph reaches here, this point, the gradient is slowly decreasing before it starts to increase again of the tangents. So if you draw tangents along this curve, I'll just draw this over here again. So this is your point of inflection, but as you can see, if you draw little tangents across the curve, the gradient is slowly decreasing, as you can see, because they're going like this, right? They're slowly getting lower and lower, until it eventually hits this point of inflection, and then it begins going higher and higher. That's why there's a turning point there, and that's why there's a turning point here, because they're getting lower and lower, and then higher and higher around these turning points. So the point at which they stop going down and start going up is your point of inflection. That is the point where it stops. So, referring to the concept of concavity, so it gives you the sketch of the diagram that it gives you initially, that it asks you to find the points of inflection for, and asks you to evaluate the reasonableness of your solutions. So if you take the solutions that we got, which are pi over 4, which will be in the center here, pi over 4, 3 pi over 4, which will be right here, 5 pi over 4, which will be here, and 7 pi over 4, which will be here, if I'm not mistaken, you'll see that as this gradient increases, if we draw little tangents across here, so they start increasing and increasing as they reach that point, so they pretty much just gradually start going up, like little tangents, until eventually they hit this point, and then they start going down, because this turning point is here, so they have to start going down from the turning point. So this is pretty much what the question is going to ask you to explain, is to evaluate that based on these points, but you can actually see if you draw little tangents, because this is an extended response question, just a small evaluate your reasonableness by giving points, but your general gist is just going to be that these gradients slowly increase as they come up, and then the moment they hit the point of inflection, they begin lowering to come over this point, and then they continue lowering, and they begin heightening again to come around this point, and they begin lowering again, if that makes sense. So that is the general gist, but you can evaluate your reasonableness by plotting it and showing that you understand what points of inflection are. That is the question. I hope this makes sense. If it doesn't make sense, please let me know. But this is the solution to this question, just a sample question I've come up with to demonstrate this concept, and I hope you have a good night. Thank you.